will finally be off of transformation of functions. Your project for transformation of functions is due a week from today. So you have another week. If you want me to take a quick look at it and make some comments without grading it, it needs to be on my desk today. So Claudia's just brought hers up. If you have it done and you want me to look at it, put it on my desk at the end of the hour. Okay. Today I'm giving you a take-home quiz, and these classes that we've covered since our last test will be on the take-home quiz. So basically classes 11 to 16. When is this due? Wednesday, right. So remember, the important things about the take-home quiz is you do it on your own. You can use whatever resources you want except for another person. And the other thing is that you show all your work in order to receive any credit. If there's just an answer and no work, I don't care if it's worth 4 points, 2 points, or 6 points, there's no credit. Okay, so you have to show your work and how you arrived at your answer. Basically the same instructions as the first quiz, okay? So let's take a look. We don't have any preview activities today. So we're going to start right in with the demonstration. And this data is fictional. It was made up. But there's what I want to encourage you to think about is there's lots of data out there that is really important data, whether it's dealing with climate change or other issues that may affect your life. The rise in student debt, increases in tuition and fees over time. There's a lot of very important data sets out there, some medical data sets that you will probably see if you read carefully enough some of the ideas that we're going to talk about in today's class. Even though this particular data set is made up, you will have a real data set dealing with carbon emissions in your class activities, okay? So there'll be a series of things that you need to do today with either a calculator, or if you have a laptop and you prefer to use GeoGebra, which is the steps for GeoGebra are much quicker and easier, then you're welcome to do this with GeoGebra as well on your laptop, and I'll help you out. Okay, but let's take a look at what the class activity today is going to focus on. It's going to focus on two ideas. It's going to focus on interpreting straight lines, very similar to what you did in your first project, but it's also going to review for you sections 2.3 and 2.4 in your book, which is all the stuff that you should know, I hope, prior to coming in, which is how do you find equations for lines? What are the 3 types of equations you can use for a line? What's true about parallel lines and perpendicular lines and vertical lines and horizontal? All of those things will be reviewed for you in the class activities. And then the main idea of today's demo, which you'll see at the top, says linear regression, and it says supplement, which means this is not in your textbook. So the information you get today will be from class. I actually used to have another project for the class based on you going out and finding your own data and answering some questions, but we took that project out. So this will be a little bit of use you have, time you have to actually model real data and try to fit what we call a regression line or a line of best fit. So some of you may have heard that before along the way, especially if you've had a statistics class. So there's a lot happening today. We'll do a little review, as I mentioned, with straight line stuff, and then I'll talk to you about the idea of finding a line of best fit. All right, so here's some made up data. Start us off, Paul. So if we measure time in years since 1987, so 1987 will be our base year, right? Base year. Oh, 1989? No, 1987 right here is our base year. Thank you. So what value of our independent variable X will we give this year, 1987? Zero. Thank you. All right. So any other year, either in the future, beyond 1987, or in the past, will be given a number based on, is it beyond 1987 or prior? So for 1989, this is going to be our x component, our independent variable. In this case, x would equal what number? 2, right? And this is going to be our dependent variable, and that will be 44. So one point that we can use right now is 244. And remember, this comes from 1989 take away 1987, which is our base year. That's how we got the 2. And remember, this talks about the percent of the country's population on a particular diet. Okay. All right, so let's take a look at the other point that's hidden in the second sentence. In 1997, 12%. So, Molly, can you tell me what point that would represent? 10, because it's 1997. Take away 1987, it's 10 years beyond 1987, and 12 because that's the percentage of the population, right? Okay, so those are 2 points. And if we were to create a graph, which would just need the first quadrant in this case, remember down here would be the number of years after 1987, and along the y-axis, our dependent variable will be the percent of the country's population on a diet. Okay. All right. So if we were just to quickly plot those 2 points, we'd go to the right 2 and up, say 44, and then we'd go to the right 10 and up 12. So. All right, so we want to find the slope of the line that passes through those 2 points. And I really hope this is just a real quick review for you. So the slope of the line that passes through those 2 points is the given. To find the slope, we use the letter M. And we know that it's the change in our vertical variable, change in y variable, divided by the change in the x variable. And another way to write change in, if you're not an English person and you're another mathematician in another country, is to use a symbol, and it's the symbol delta, which is a Greek letter. The change in y over the change in x can also be written that way. So we're going to find the change in the y value, which is going to be to subtract the 2 y values from each other. And we're also going to find the change in the horizontal distance, the x values. Okay. So again, it doesn't matter whether you say y2 take away y1 or y1 take away y2. It's just the difference in the 2 y values. What's critical is if you use y2 first, then what's going to be the first x value you use here? X2, right. So when you look up and down, partners go together here, y2 with x2 and y1 with x1. And again, it doesn't matter which of these points we call x1, y1, or which one we call x2, y2. So I'm just going to call this one x1, y1, and this one x2, y2. Okay, so I'm just going to do a little erasing here to give myself some room. All right, so the change in our y values can be seen by this vertical distance right here. So this is at a height of 44 and at a height of 12. So the change in my vertical distance can be written as y2 take away y1 over x2 take away x1, or as I mentioned, y1 take away y2 over x1 take away x2. Either way. So if I look at this height, I'm going from 44 down to 12. So that's a drop. Okay. That's negative 32. That's a change of a height of 32, right? Okay, now let's take a look at the change in our horizontal variable. Right, delta x would go from 2 to 10. Okay, but I'm looking at y2 and x2 first here. So I'm going to start with 10 and subtract x1, which is 2. So that's 8. So the first thing you should notice is that the fraction you get, or the ratio that you get, in fact, it's a rate because the units are different. So that's the difference between what we, excuse me? That's right. Yeah. That negative 32 divided by 8 is going to be a rate because the units in the numerator and denominator are different. So the first thing you want to notice is that this is negative, and notice that the slope of your line is negative. So that's always a little test for yourself. That's the reason I put these 2 points on here real quick, is because before you even do your slope calculation, you want to make sure that the sign of your answer matches the slope of the line, whether it's negative or positive. Okay, just as a little kind of built-in check for yourself. Now, if we put the units on this right now, the 32 is a change in our dependent variable, which is a percent, and the 8 is a change in our years since 1987. So you could say that the country's population that was on a weight loss diet decreases, because I see the minus, 32% over an 8-year period, right? But most of the time we talk about slopes, we usually like to refer to them as a unit rate. And a unit rate means your denominator is 1. So that's usually our preferred way. It doesn't mean you couldn't discuss what the slope means just as you see it right there with minus negative 32 divided by 8. But if we reduce that, if we get a 1 on the bottom, that means we divide 32 by 8 and we get negative 4% per 1 year. So usually when we interpret the slope as a rate of change in the context of a story, we often will talk about it as a unit rate. It's not necessary. It's just usually what people do. Okay. So does someone other than Ian want to give us a shot at interpreting the slope as a rate of change in this particular context? You had a lot of practice with Project 1, so hopefully you feel okay about it. Woohoo! All right. Every year, see, I told you there's a 1,000 ways to write this sentence, right? Every year after 1987, there's a reduction. Is that what you said? There's a 4% reduction in the populace, ACE, really, populace participating in the weight loss plan. Okay. So what's important is that I can read the sentence and I know the context of the story. I know what each number of the slope means and its unit. So we can see the fact that it's negative is taken care of with the word reduction. That takes care of the negative sign. The 4% in the numerator is right here. And every year after 1987 is represented right here. Okay. Now, there's 20-something people in this classroom. You would all probably write that sentence slightly different. But what's important is that I could read your sentence and I would see this rate or some other equivalent rate from the context in your sentence and know what the data represents. Okay, that's what's important. So you'll always need to use both numbers and units in the context of the story. Okay, so let's find the slope-intercept form of the line that joins these two. Now, slope-intercept form, we've already got an important part of that, which is -4. So right now we need to find B, which is our y-intercept. B is the value, it's the y value of our y-intercept. So in order to find B, if we need to solve this equation for B, we can't do it right now because there's 3 unknown parts. So to find B, you have to take a solution or a point on the line and fill in the x value and the y value. We happen to know 2 points on that line, 244 and 1012. So it doesn't matter which one you use. Okay, so in the first class I used 244, so just to do something different, I'm going to use the point 1012. Now, the only thing you have to be careful of, and this is the little mistake students can make, is because y occurs first here in the equation, sometimes people put the very first thing they see. But remember, this is your x value and this is your y. So I'm going to put 12 in for y and 10 in for x equals negative 4 times 10 plus b. 12 equals negative 40 plus b. B equals 52. So that tells me that the overall equation for this line would be y equals negative 4x plus 52. This strategy of finding a missing part of an equation you'll use over and over again, even as the type of equation or function changes throughout the course. When we come to quadratics, the same thing will be used. Come to exponential functions, the same idea will be used. You take a known point, which is a solution to the equation or the function you're trying to create, and you throw it in to your equation and solve for the part you need to solve for. In this case, it's the y-intercept. Now, someone in my previous class said, couldn't I just kind of look at my graph here and figure out what my y-intercept is? And I said, sure. Because as we move along each year in time after 1987, we were decreasing by 1. Now remember, this point right here, 2 represents 1989. I need to get back to 1987, which is the year 0. So instead of decreasing my y value by 4%, what would I do if I'm going back in time? Increasing. So if I went back to my point located at 1, it would be 148, because I'd add 4 to 44, and then to go back one more step, I'd add another 4, and I'd get to 052. So if that's how you do it, which would work okay this time, but if your numbers were, if you had points that were further out in your domain, it might be hard to get back there without an algebraic approach. But if you did something like that, just make sure you show me the work for how you got there, or write me a sentence, okay? So I went back 2 years, so I added 8% to 44. That would do it for me. That would be okay. All right? Unless I said algebraically find versus graphically. So explain the significance of the y-intercept. Okay, if we write the y-intercept down, just the coordinates, this is where if you just put in your units years after 1987 and percent of country's population on a diet, right underneath them or beside it, however you want, you can read your story to interpret that. Okay. So how about someone from this room, either table side of the room, table 1 or 2, want to interpret the y-intercept for us? All right, so the y-intercept predicts the what did you say? Oh, the percentage of people? And what percentage is that? 52% has to be in there. The number 52 has to be in there in 1987. And remember, the 1987 corresponds to x being 0. Good. Thank you, Ira. All right. So one of the equations of a straight line that you will be working with in sections 2.3 and 2.4 in your book is the one, if I asked you, what's the equation of a line look like, I'd have what we call the chorus effect. Everyone would say y equals mx plus b, because this is the one, I don't know, that you use probably the most somewhere along the line. However, there's 2 other forms. One you'll be introduced to in your class activities. The other form is called point slope. So notice, so if you look at the language, this is called slope intercept because you're given the slope and the intercept. Slope negative 4 divided by 1, intercept 52, 052. Here, you're given a specific point, the values of a specific point, and the slope. So To find the point slope intercept of this line, I already know that models the percentage of adults. I already know that m is -4. And now all I have to do to finish this equation off is to pick any point that lies on that line. So I know 244, is that the right? 244. So again, 44 is the y value, so I've just got to be careful to put it in the right order. The 44 comes first, and then the x value is 2. That is the point slope form. I don't have to do anything to this point slope form. That's it. All right. Now, if you look at this, what you want to be able to do is to interpret what that means. This tells you the slope, and it gives you a point on the line. So you got to be able to look at this thing and say, oh, I know my x value is 2 and my y value is 44. Okay, what if I had a y plus 44 there? What would that tell me about the y value? It's negative, because the point slope form of a line always has subtraction in it. So if you see an addition, that means either your x value or your y value is negative. And this is just a variation on your slope formula. Look, if you divide both sides of this equation by x take away x, the quantity x take away x1, you basically are looking at your slope formula. All right. So G is just going to ask us to take this point slope form and put it into slope intercept, which you're more familiar with. So y take away 44 equals -4 times x take away 2. Let's put this in slope intercept form. So what would you do first if you want to put this in slope intercept form? Remember, slope intercept form says solve this for y. We want y all by itself. So what would you do first? Kelsey, what would you do? Okay, you distribute. Okay, let's do that. -4x plus 8. Okay, and Angela, what would you do next? Okay, and what would you do to do that? Yeah, add 44 to each side. And voila, you get exactly the same thing we got in part E or part D, whatever it was. Okay. So it's only based on our probably the experiences you've had in previous math classes that say that's the form of the line that I want to see, but either of those two equations say exactly the same thing. They're equivalent. So if I ask you for the equation of a line, you could give it to me in the point slope form or the slope intercept. Now usually, so this is what we did in project part 1. We used our model. Remember, this is a model here to predict we could either predict the percentage of the population on a diet given a specific time, or we could find the time a certain percentage of the country was on a diet. So use your slope intercept form of the equation to predict the percentage of adults on a diet in 2000. So the first thing I need to do is to take 2000 and write its corresponding value for x, which is the number of years after 1987, which is 13. So that tells me x is 13. So now I take the slope intercept form of my line and put 13 in where I see x. And what does that say? What percentage is on a diet in 2000? 0%. Right. So that's where our line would come down and intercept the x-axis. Okay, in what year was 50% of the country's population? Well, we could probably do this without any algebra because we know in 1987 it's 52%, and 1 year later it's 48%, right? Because it drops 4% each year, and 50 is halfway between that, right? So it's going to be halfway between 1987 and 1988, so midway through the year. So let's see if that works for us, if the algebra will tell us the same story. So now 50% is our y value, so I put a 50 in, and I get -4 times x plus 52. And I'm now trying to solve for the year after 1987, so I'm solving for X now. It's always important to know which of the variables you're solving for. I subtract 52 from both sides, and I divide both sides by -4. So X is 1/2 year after 1987. So halfway between 1987 and 1988, 50% of the country's population will be on a diet. Okay. Any questions on answering any question like that? If I give you the equation for a straight line, or I ask you to find the equation for a straight line and then do some interpretation of slope, y-intercept, and then do some predictive measures on it. Any questions at all? All right. So now we're going to start to work our way towards the idea of linear regression or line of best fit. So if we assume that the percentage of adults on this particular diet is reduced or declines by 4% every single year, no variation in that percentage, then our data would look like this. If we do it, what we call a scatter plot in statistics of the data, it would fall, every single point would fall as each year went down, the height would change by 4. Means we have a drop of 4% in the number of people, the percentage of people on this diet. Okay, but guess what, folks? Real data does not look like this. You go out and you measure real data from year to year, whatever you're interested in, whether it be the number of alternative fueled vehicles in the last 20 years, you would not see it lining up in a perfect line, whether that line has a negative trend or a positive trend. Right? So what you would see is you would see something that looks more like this. Okay, you would see your data scattered about a little bit, and you hope that you can look at your data and figure out what kind of shape, what kind of graph would help describe that data. And when you look at this data, you see, well, the direction the data is going in, as my years increase, my population decreases. So one thing you get a sense of is the direction of the data. As X increases, your population, the percent of your population decreases. So you get a sense that the direction here is going to be negative because they're acting inverse to each other, inversely. You also see that the general shape is linear, so your shape is linear. Okay. So then what you really hope to do is to try to somehow see if you can model this data with a line. Okay, some type of line, predictive line, or a line that estimates certain values within that data range. Okay, so if we took the 2 points that we chose to start off this demo today, 244 and 1012, that's the line that you would draw between those 2 points. And I don't know, what do you think? Does that look pretty good? Yeah, you can see that the points are sort of clustered about that line. I don't know if it's the best line through there, but what I'd like you to do right now is use the rulers on your desk or your Math Studio bookmark or the edge of your, whatever you have on your desk, and draw what you think might be the line that fits that data better than that line. Okay, if I asked you what your strategy was as you started to draw this line, what would you tell me? What was your strategy as you started to draw your line? Were you thinking about anything, or you just kind of just put a line in there? Yeah, Victor? Okay, so you were trying to look for a line where you had a certain number of points above the line and below the line. Okay, that's an interesting idea. Anybody else? Okay, nobody else wants to vote. Yeah. Okay, yeah, an average, the average distance of points above the line and below is about the same. Good idea, yeah, because if we looked at those distances, if we called one positive and one negative, when we add them together, they should be about 0, right? Okay. All right, so if I took all of your lines, I had you all come up and put your lines on this scatter plot, then we might get something that looks like this. So the big question is, how do I decide which line is the best line? Okay, so you've already started to give some ideas about what our calculators and computers do for us in terms of finding that line. And I always have to control myself because for many years I taught statistics, and I love to show all of the stuff about how this line gets to be this line, and talk about the idea that both Victor and Kelsey just shared with us about this distance above the line and below. And I'm just going to show you with one teeny little example. If we took the distance from this point to the line and I made that vertical distance, that's called a deviation. It's how far is that point from the line itself, okay? But there might be another point somewhere on there that if I drew the vertical distance from the point below the line to the line, then they might offset each other, because if I gave one idea a plus and the other a minus deviation, they would all add up to 0, and that's not going to help me find the line. So the idea, and I'm just going to do this real quick. I used to have a little what we called an applet that used to do this. The idea is to find a line, and this is what we call the line of best fit, or the least squares regression line. I'm going to write that out for you. Least squares regression line, because that's where you can see what I'm about to do. So this particular line is the only line, it's unique, that minimizes, that's where the word least comes from, the squared deviations above and below the line. So in other words, if you took this first line right here from 0, 57, the vertical distance down to the line, and you made a square. So in other words, I made a square of exactly, and I'm not going to be able to do it exactly right, but let's say that square, I made a square. There's an area to that square. Areas are positive, yes? So now if I take this deviation and make another square, like this, and I did that for every single little deviation. Now look at this, 244, that square is going to be teeny, right? And look at this one, 10, 12, that's even going to be teenier. So this line minimizes the areas of all those squares. Okay, that's what your calculator does for you when it finds you the least squares regression line, or the line of best fit. And if you put any other line in here, then it's going to make that the sum of those squared areas bigger than the sum of these squared areas. Victor? The slope of I'm going way back. The slope of the regression line is what we call, is found by the correlation coefficient times the standard deviation of your y variables over the standard deviation of the x. And then I'd have to look at all of the calculations to get each of those to see if that's exactly how it's done. So I can't quite answer that right now because it's been a long time. I just remember the formula for finding the slope. There's a lot of mathematics involved in it. So, you know, people sometimes, students complain to me, like later on, you'll be going through the steps with your graphing calculator and you say, oh, there's too many steps, I can't remember it. Well, if you were taking this class in the dark ages, like when I took it, we had no graphing calculators. We had to do all of this by hand. So please don't complain because life could be worse than punching some numbers into a calculator. We didn't even have laptops or personal computers then. I know, I'm really old, but you know, it used to be, talk about tedious and grunt work. It was crazy, all right? So anyway, this line is called again, the least squares regression line, the line of best fit line, and there will be a unique equation for it, and it's right here. So again, remember, this is a predictive, this is a model, okay? I put that little hat on it to remind us that we're predicting or estimating values based on this line. Now, one more important idea, you just heard me say to Victor that the slope of this line was something called the correlation coefficient, which is this letter R, correlation coefficient, times some other kind of weird thing called the standard deviation of y and x. Okay, that's all stats, you don't need to know that. But the correlation coefficient is a very important idea. And what this correlation coefficient talks about is it tells us the strength and the direction, both. So this numerical measure tells us the strength and the direction of the linear relationship between these two variables. So that's what you need to remember. It's the strength and the direction of the linear relationship. So our R value, which is the correlation coefficient, is always between -1 and +1. Where -1 and +1 is that perfect fit, the perfect correlation. Things line up perfectly in a straight line. If it's 1, it's going in the direction of a positive direction. As x increases, y increases. If it's -1, it has a negative slope. As x increases, y decreases. So instead of this little chart, I found a nice little app, nice little website this morning, because I had a student that kept asking interesting questions. He really was interested in the correlation coefficient. And one of the things that students often ask about is, how do I know whether an R value of like 0.6 or an R value of -0.6, is that a strong association or a moderate? So this little diagram here helps you think about this. Again, if you're -1 and 1, you can't get any stronger. If you're getting very close to 0, your strength of your linear relationship is getting really weak. In fact, it might say you better look for another model, because a straight line isn't going to be a good model for you to use as an estimate or a predictor. And then really, depending on sort of what academic area you're from, the social sciences will tend to move the moderate correlation a little closer down here than, say, the hard sciences would, like your sciences like biology or health sciences or what have you. But psychology and sociology, this kind of moves, this moderate positive or negative correlation moves. And in fact, there's a historical context. This has changed over time. So, and then if you're interested, here's some different scatter plots. And here's what it would look like if you had a 0 correlation. There's no direction given to you there at all. In fact, you could draw a line anywhere here. That would have a 0 correlation. This would be about 0.5. You see the scattering about the line. A stronger positive correlation. You see how the cluster is getting closer and closer to the line. And here you're getting really close. This is really strong, getting close to R of 1. Similarly, with your negative, again, 0.4, moderate. 0.65, the cluster is getting closer to the line, the cluster of points. And you can see that they get closer and closer with these negative correlations. Yes. Yeah. So if I had asked you to do a project, I would have I asked when you do a project that your correlation coefficient's bigger than 0.6. That's what I used as a cutoff. And you can see here that 0.65 is a moderate association or a moderate correlation for strength. All right, so I think that pretty much does it for what we need to do today. Your class activities will take you through lots of different things. I will stop you at 11:35 to ask you to start working on this carbon emissions data and using the directions for the calculator to find the line of best fit and going through the steps in your calculator. Any requests for music?